Okay, so if we have the same index and the same radicand, remember what the radicand is, that's the number inside the square root or inside the radical sign. We can only add those if the index and the radicand are the same. So if we take an example of what a like radical is, 2 times the square root of 2, 3 times the square root of 2, the square root of 2, and negative 7 times the square root of 2, those are all like radicals because they all have the square root of 2 in them. And similarly, when we have different roots, like the cube root of 3, 2 times the cube root of 3, and negative 10 times the cube root of 3, those are like radicals as well because they have all the same radical there. Now, unlike what I talked about with polynomials, those are variables. These are actually numbers, right? You can put the square root of 2 on the number line. It's about 1.4. And they're numbers, but they're numbers that have a special form, in the sense that they have the square root. And so we only will add the ones that are similar. This holds true for variables too. So if we have the square root of x, that would be a like radical to anything that involves the square root of x. So to add and subtract these, we basically take the number that's multiplying those radicals and treat those like a coefficient, and we add those. So if we have the square root of 2 plus the square root of 3, we get 4 times the square root of 2. If we have a mix of radicals, like the square root of 3 plus 4 times the square root of 2 plus 7 times the square root of 3 minus the square root of 2, only the ones that are like radicals combine. And so you might end up with an expression like this where when you extend this you get, you add the square root of 3, we have the square root of 3 plus 7 times the square root of 3 makes 8 root 3, and then we have 4 root 2 minus root 2 is going to be 3 root 2. So there's nothing we can do at this point then with the square root of 3 and the square root of 2 to make this any simpler. So very often you have to simplify before you add these together. For instance, if you have something like the square root of 20 plus the square root of 45, those are definitely not like radicals, right? They have the same index, right? They're both the square root, but 20 certainly is different than 45. But that doesn't mean it's the end of the game. What you have to do is first simplify this, and you do this by factoring. You can factor 20 into 2 squared times 5, factor 45 into 3 squared times 5, take out that 2 and take out that 3, and so now we have 5 times the square root of 5. Okay, is everyone following? I'm not going too fast here? No? Okay? You're good with it? Okay, so let's look at a few examples, and they'll get progressively more difficult. So basically, if they're all the same radical, we just add up those leading numbers as coefficients. So we say 2 plus 5 is 7, minus 1 is 6, plus 3 is 9. So this thing simplifies to 9 times the square root of 2. So now if I have a variety of things, the square root of x and the square root of 2, I can only add the square roots of x together and the square roots of 2 together, so I get 7 minus 3 is 4 times the square root of x, and then 2 plus 1 is 3 times the square root of 2, similar to the one that I had on the previous slide. And so you should always look to simplify, and so if we say 8 times the square root of 27, that simplifies into, or we factor the 27 to get 3 cubed, and then we can take out one of the 3's, and 3 times 8 is 24, so we have 24 radical 3 minus 3 radical 3. Excuse me, and we have then 21 radical 3. And here's one with a variable in it. So we factor this out to be 5 squared y inside the square root, and then the square root of 8 squared y. You get a 5 and an 8 outside of the square root of y, and those add together to get 13 square root of y. And so another example of simplification here is that we're going to take 8 times the square root of x cubed plus x times the square root of 81x. And so the same strategy there. We factor this out, or we simplify this. So now this becomes, instead of x cubed, it becomes, we take this x squared out of the radical to x, and then we have this x squared left. And now we have two things that we can add together. And notice that x square root of x is in common in both, so we're just going to add the coefficients together, and we get 17x times the square root of x. Okay, so time for you to try a few. Okay, there's lots to try. Okay, so that first one, we just, take out the 2 squared and the 3 squared. And so 2 plus 3 is 5. How about the second one? The second one, we factor it the same way. The thing that we're left over with is we can take out a 2 out of that 2 squared and a 3 from the 3 squared, but we end up with dissimilar radicals, so there's no more that we can do there. This next one, we get almost exactly the same thing. We can simplify the square root of 12, but that only goes to, well, that's the square root of 3. The other one is only square root of 6, so we don't get that. Okay, I'll let you work a little bit longer to get the other two now. Okay, so Monica, did you get this one? The square root of 20 plus the square root of 5 minus the square root of 10?
Is it 3 root 5 minus root 10?
Yeah. Okay, that's the first part. Simplify it. 3 root 5 minus root 10. Okay, everybody get that? And how about the last one? Allison, did you get that?
Yeah, I got 13 root 3x.
Root 13 root 3x. Great. Anybody didn't get it? Anybody confused about the steps there? Where you start with 12x inside that square root works out to 4 times 3x, and so the square root of 4 is 2, and so we have 2 times 4 is 8, is how we got that coefficient there. And then, of course, with this one, we have 25 times 3, so the square root of 25 comes out as a 5, and then you add your 8 and 5. Okay, a few more examples. The ones that I've done so far involve all square roots, and so these involve cube roots now. And so, really, the only difference is in the simplification process is probably just a little bit more tricky, but the process is the same. So the first thing that we're going to do is we factor the what's inside the radicals, and we see that 54 is 2 times 3 cubed. So 54 is actually 6 times 9, right? And so we have 2 times 3 times 3 times 3, so that's 2 cubed. That second term doesn't simplify at all. So when we take that 3 cubed out of the cube root, we have, and then take a y cubed out of there, we're left over with 2y squared inside the cube root. That matches the second term, and so we can add these. Now, we add these, you take 3y plus 4, and there's not much you can do other than that. And so this is simplified from the standpoint that our radical, the square or the cube root of 3 2y squared is all, you know, in one place. We only have one instance, and that's really what we're trying to do here. But you can also make an argument that this is already simplified from the standpoint that we don't have any parentheses, right? I mean, you can think of simplification as removing all your parentheses, and in the first 2 weeks of class, that's what we did. We had these algebraic expressions that we just multiplied all out, so we get rid of our parentheses. Now we're looking at expressions that, you know, we have some parentheses involved because of the way we do this grouping. So it's not necessarily that one is always superior to the other. It really depends what you're looking for. The second one is what we're looking for in this context, but ultimately, you know, you can really say that 3y doesn't add to 4 and get you anything simpler than something with parentheses. So, you know, a little bit of this is a matter of interpretation. Okay, so then we have another one. 4 times the 4th root of 48 minus the 4th root of 243. So the first step, of course, is factoring those, and so what I often do is factor using the successive division. So I start out with the smallest prime number, which is 2, and I say, okay, 2 times 48, and keep on dividing by 2 until I can no longer divide by 2, and then if I had something more here, I would be dividing by 3, and then 5, and 7, and then 11, and just keep on going up each of the prime numbers. So if I did that with 243, 243 is not even, so I'm going to start with 3 and successively divide it by 3 until I'm done. And so there I have 5 3s, and so I can rewrite this in exponential form as 2 to the 4th times 3 and 3 to the 5th, both inside those radicals. And so now I can remove my groups of 4 out, and I get, I take a 2 out of this one here, and so 2 times 4 is 8, and then here I'm going to take out a 3, and so 3 times 1 is just 3, and now I have those two that have a similar radical, and so I can make it 8 minus 3 is 5, so I get 5 radical 3. Okay? Am I going too fast? Yeah. Okay. So here's several for you to try. These are a little bit harder, so I would suggest you work with somebody sitting around you and see what you can come up with here. And then we take out the 3's. And so we get 6 times the cube root of 2 plus 24 cube root of 2, and just what Michaela said, 30 cube root of 2. How about this next one? Everybody, did anybody finish it? Do you need more time? Or this one is by far the hardest, okay? So there's a couple different routes that you can take with this. So let me do this on the board here and show you the way I did it that I think is the shortest way. And then there's kind of the, you know, the step-by-step way that we were talking about, that I've talked about earlier in simplifying things, and you ultimately get to the same place. But if I consider just that first term of the cube root of 6x over 24, if I factor that first, now here I'm departing from what I usually recommend, that just split this into two different ones. You can also say, well, 6 and 24, we can reduce this to x over 4, and we'll take that route as well. But here I have the cube root of 2 times 3 times x over 2 squared times 3, excuse me, it's going to be 2 cubed times, times 3, like that. Was there an x in there? I guess that was it. Okay, so what I'm going to notice is that my 3's cancel out, and that I can cancel out one of these 2's to make this 2 squared, but then the thing I'm going to have to do is turn around and rationalize it. So I'm going to be multiplying it by the cube root of 2 to get more 2's in there. So let me just simplify this as, now, like this, and so this turns out to be, no, it's the cube root of 8, which makes it 2. Okay? So that's, to me, one of the faster ways to do it. But if I followed, all along what I'm suggesting you do, it's not the end of the world. In fact, you get there quite nicely. Like that, right? And so then we're going to say the 2 is going to come out here, and we're going to end up with the cube root of 3 over 3. Now I'm going to rationalize this by multiplying it by the cube root of 3, I need squared, right? Well, in order to make that 3 cubed, and then I'll multiply the numerator by exactly the same thing. And so when I multiply all this out, I get, on the bottom here, I get 2 times 3, makes it better, 3. And on the top what I get is the cube root of 2 times 3 cubed x. And of course I can take out this cube now to be a coefficient, so I got 3 times the cube root of 2x over 2 times 3, and now my 3's cancel, and I get the cube root of 2x over 2. So you see I came to the same answer, just a couple more steps, and this is kind of the way that we do most of them, because most of the time it's the most direct route. But this one you can recognize that you have a 3 to cancel, and that you don't cancel these because you really do like that 3 in the exponent, okay? So that's just the first half. The second part, that doesn't simplify, so if I just go through and kind of do what I did. Okay, so you recognize that when I get to this part, that's the same thing as 1/2 times this, right? Because I can, these are the same things. And so then, now I have like terms, and so I'm going to take that 1/2 plus the 4 to get 9/2. And so there's my answer. How did you do with that one, okay? Or was that...
I did like a way I thought was working, but I got a completely different answer.
So where did it depart?
First I factored 24, so I had like the cube root of 6x over 2 to the 3rd times 3,
Mm-hmm.
and then plus 4 cube root of 2x, and then that equals, so I pulled out the 2, so I had 2 times the cube root of 6x over 3, plus 4 cube root 2x. And then that's when I simplified and I got 2 cube root of 2x plus 4 cube root of 2x, and I got 6 cube root of 2x. And I
Yeah,
got a little bit
let me
wasn't supposed
take
to
a
happen.
quick look. I think what happened was when you pulled out that 2 cubed, you didn't continue here. Let's see, so you got, yeah, the 2 is actually in the denominator here, right?
Oh,
So that
okay,
should
so it
be
doesn't, okay.
1 over 2, and then you'll get the right answer.
Perfect, thank you.
How did you get the 9 again?
4 plus 1/2 is 9 halves. So 4 is 8 halves. 8 halves plus 1/2 is 9 halves. Okay, so occasionally what you have to do, like we did with this one, is that we have to rationalize before simplifying. And that particular one didn't really stand out as having to do this. I mean, certainly as you work this, you would recognize that, but occasionally it just looks a whole lot simpler than that. So if we have the square root of 3 minus 4 over the square root of 3, we do have kind of a similarity here with the square root of 3 appearing in both terms. But it's not quite the same thing because we have this 4 over the square root of 3 rather than something times the square root of 3. And this is probably one of the most compelling reasons why you want to rationalize. So if you rationalize this, you take that second term and multiply it by the square root of 3 over the square root of 3, we would get 4 times the square root of 3 over 3. Now, I know sometimes envisioning what's happening with these fractions can be difficult, but when you have an expression like this, where I'm going to say just part of this, 4 times the square root of 3 over 3, that's exactly the same thing as 4/3 times the square root of 3, right? Because if I were to transform this again, I could make this into negative 4/3 times the square root of 3 over 1, which brings me back to this. So seeing the coefficients when you have a ratio like this as just a fraction times your similar term oftentimes helps you, look to see what you really have here. And so since I have 1 minus 4/3 is what this boils down to, is I'll have negative 1/3 times the square root of 3. So 1 minus 4/3 is, that's 3/3 minus 4/3 is negative 1/3. So if we have something a little bit more complicated like this, where we have square root of 12x minus x over the square root of 3x, we want to first simplify that first term and then rationalize the second term. And so when I do this, I can take out the 2 to end up with 3x, and then my simplification here, I have, or the rationalization, I have x times the square root of 3x divided by 3x. So now I have a similar term, okay? I have the square root of 3x here and the square root of 3x here, and I also have x over x. So those x's cancel. So what I really have here is 2 times the square root of 3x minus 1/3 times 3 times the square root of x. Okay? And of course then 2 minus 1/3 is 5/3, because 2 is 6/3. 6/3 minus 1/3 is 5/3. Okay. Of course, it's time for you to try some. Now, in the earlier class, a lot of people struggled with this square root of 1/2. So what I would do here first, just to put this in a form that you can deal with a little more easily, is separate that fraction. So you have the square root of 1 over the square root of 2, which amounts to 1 over the square root of 2, and then it'll be familiar. So use that as a start. So I'll just do it out. So the first thing that we want to do is get it to a factored form, and then that square root of 1/2 is the square root of 1 over the square root of 2. And we can now simplify that first term to be 4 radical 2, right? Because I can, the square root of 2 to the 4th is 4, and then I have a 2 left over. And then I'm going to rationalize square root of 2 over, or 1 over the square root of 2. If I multiply that, and I guess I should have shown the one step here. If I multiply that by square root of 2 over 2, square root of 2 times square root of 2 is just 2, and so I have the square root of 2 over 2. And this is the same thing as 1/2 times the square root of 2. So now I have 4 times the square root of 2 and 1/2 times the square root of 2, and you add those together and you get 9/2, right? Because, back up. Because 4 is actually 8/2, and then you take your 8/2 plus 1/2 and you get 9/2. All right, now rationalize with variables as well. And so the first one I'm going to multiply by square root of 5 over the square root of 5, and I get 2 times the square root of 5x, I should be saying, over 5x. And that now is similar to this square root of 5x. The question, though, then, is how do we add these? We can say there's 2 ways to do this. I can put it over a common denominator. So, oops, wow. I can put it over a common denominator by multiplying the second one by 5x over 5x, and then I'll get 2 plus 5x times the square root of 5x over our common denominator. That's one way to do it. The other way to do it is if I recognize that in front of my 5x I have 2 times, or 2 over 5x times the square root of 5x plus the square root of 5x. This is the same thing then as saying 2 over 5x plus 1 times the square root of 5x, like that. So that's an alternate form for that. They're exactly the same. And of course, if you take the common denominator here, you'll see that this is going to be 2 plus 5x over 5x. So we're ending up the same place ultimately if we make a common denominator. Okay. So that's about adding radicals together. Your homework will consist of the work up until this point. Now I have, we'll start in on multiplying, and I want to show you a couple slides here. You're not going to have homework on this, but we're going to just start where I'm leaving off right now on Monday to get into multiplying radicals. So when we're multiplying radicals, what we do is if we have the same index, we can just go ahead and multiply the numbers and put them under the square root sign. And where this comes from is that exponent rule that we said that when we have a something to the nth power times something else to the nth power, we can multiply the 2 numbers together before we take to the nth power. And so think about this as being like 5 to the 1/2 power times 2 to the 1/2 power would be 5 times 2 all to the 1/2 power, which is 10 to the 1/2 power. So when you're doing this, and you can look at something like square root of 2 times the square root of 50, You have two choices at this point on what to do. First, you can just go ahead and multiply them together and then see if it simplifies, or you can simplify first. Now, here's one of those cases where probably just multiplying together is a little bit easier, because what we're going to do is we're going to get the square root of 100, and that's easy to see. That's just plain old 10. Now, if we did it the other way around, and I'll do this one on the board as well, if we have the square root of 2 times the square root of 50, the square root of 50, it factors into 2 times the square root of 5, or 2 times 5 squared, right? That's 25 times 2 is 50. So then this goes to square root of 2 times the square root of 2. Oh, that was a phone, yeah, okay. And then you have the square root of 5 squared, which is times 5. And then the square root of 2 times the square root of 2 is 2 times 5, and we end up with 10. So there's a few more steps involved by simplifying before we multiply. So while when we add, we always want to simplify first. With multiplication, it's not necessarily required or even easier to simplify first. Okay, so all the rules of algebra apply to radicals as well, and so when we have something like this, the distributive property of multiplication over addition works, and so we just do it term-wise. We say 3 times 2 is 6, and then 3 times the square root of 3 is just the square root of 3 over, or 3 times the square root of 3. So it works like you would expect. Now, if what you're trying to multiply is a radical, it works exactly the same way. So we're going to take 5 times the square root of 3, and then we're going to add that to 3 times the square root of 3, which is just the square root of 9. Square root of 9 is, of course, 3, and we end up with something that has still radicals in it, but it's in the opposite order, where the first term now has a radical, second one doesn't. And so this kind of thing where we can eliminate radicals through multiplication by simplifying multiplication will turn out to be a way that we can essentially get rid of radicals in certain rational expressions. Okay, so that's where I want to stop. And that's where we'll start on Monday, probably right from this very